Thank you very much to the organizers for the invitation. This is my first time at IHS. Very beautiful, nice here. So I'd like to talk about invertible topological phases and anomalies, and I'll be kind of going between the lattice, kind of more condensed matter viewpoint, and quantum field theory. And here are a couple of references. That will cover at least some of my lectures. And then Witten. Or at least have an overlap with some of my lectures. Okay, so I'll begin by talking about gapped phases of matter. And you might ask, well, why study gapped phases of matter? So first, they exist. And they actually, some of them have even been found in the lab, like the quantum Hall effect, topological insulators, perhaps even some spin liquids. So that's the first reason. Second reason is that they're simpler. we can make a lot of progress, but they already, even though they're simpler than, say, general gapless states of matter, they're still very intricate, so very rich. And the third reason is that they give us a window into more broad class of phases of matter, including gapless phases of matter, and that happens through a variety of ways. One of which is, if we take a gapped bulk and study its boundary, sometimes the boundary has some protected edge modes. And in the case of invertible topological phases, which will be the main subject of my lectures, we will see that they will possess boundaries that have a Toft anomaly. So in the bulk, we'll have an invertible gapped phase, and on the boundary, we'll have something that carries a Toft anomaly. So that's where we are kind of building up to go. Okay, but first let me introduce the general setting that that we wish to explore. So we'd like to understand lattice systems, right? So I take your favorite lattice in some number of dimensions, and first of all, kind of the preliminaries, we will consider systems where the Hilbert space is a tensor product of local Hilbert spaces over the sides of the lattice, and each lattice side will carry a finite dimensional Hilbert space. And we will consider a Hamiltonian on this acting on this Hilbert space, which is a sum of local operators. So Hi is localized near some site I. Okay, and we will begin by talking about Hamiltonians which are gapped. So what does it mean for a Hamiltonian to be gapped? Well, we begin by studying the spectrum of the Hamiltonian on some L by L lattice. Let's, for definiteness, or L to the D lattice, for definiteness, say that we choose periodic boundary conditions, and we look at the spectrum. And okay, the spectrum might look something like this. Well, maybe there's some dense set of levels here. Then there are a couple of low-lying states. And then we take the system size L to infinity. So we take the thermodynamic limit, and we might end up with a situation where in the thermodynamic limit we have some k-fold degenerate ground state, and it's separated from everything else by a finite gap delta. So delta is the gap. So if we end up in a situation like this, where let's for definite say that k is finite, we will call that a gapped Hamiltonian. Contrast with the gapless situation, where we cannot define the gap, where the gap is 0. So now we say that two Hamiltonians H1 and H2 belong to the same gap phase if there is a continuous path in the Hamiltonian space between them, along which the gap delta doesn't close, remains finite. So H1 and H2 belong to the same gapped phase if we have a family of Hamiltonians. Let me call it H of S. That interpolate between H1 and H2 as S goes between 0 and 1, and the gap delta remains non-zero for all S. So this is an equivalence relation on the set of Hamiltonians. Now, we also define what we mean by a trivial phase. And a trivial phase is one which can be continuously connected to a product state. Right? So trivial phase so consider a Hamiltonian H naught, which is something like this. Where phi is some particular state in the side Hilbert space. Right? So say you have a spin 1/2 on each side. If all the spins point up, this is a product state, right? It's completely disentangled, and this is a representative of the trivial phase. Okay. Now, so everything here is in terms of lattice system, but at least to me, a big surprise is that a very large class of gapped phases on the lattice are described by topological field theory.
Max, can I ask you, so you have this K there, does it mean that there can be several degenerate ground states?
That's right, that's right. For general topological phases, there can be several degenerate, or general gap phases, there can be several ground states.
And when you define equivalence, you also require that these states, K degenerate states, they remain degenerate along the evolution?
That's right, because otherwise suppose one of them gets lifted up a little bit, right? And the gap, as it's lifted up, the gap goes to 0.
Max, can I ask you?
Yeah.
The generacy k. This is the you start in finite volume.
That's right.
And then take the limit, and then you see how many
That's right.
things collapse. So.
That's right. Exactly.
May I ask?
Yeah.
So the spectrum depends on like boundary conditions, for example.
That's right.
Would you impose that condition for any choice of boundary condition, or is it always relative to one specific choice?
So it might generally what we find is that let's say. Okay, first of all, for lattice systems, it's very difficult to choose boundary conditions for general lattice systems, it's difficult to choose boundary conditions which are different from just periodic boundary conditions. In some cases, maybe when you have a theory which is defined not on the lattice but in the continuum, maybe you can put it on a more general manifold, but it's hard. So in practice, what we have to work with is tori of various dimension. But philosophically, it can be that you put the system on manifolds with different topology, and this number k changes. But at least for each topology, the number k should be stable.
But what about the gap? What if for one boundary condition you always have a finite gap, but for a different choice of boundary condition the gap becomes like 0?
So we will be working with closed manifolds. So for closed manifolds, we want the gap to remain finite, independent of boundary.
The 0 mode with anti-periodic boundary conditions, you kill the 0 mode, for example, something like that.
No, but here you see we already took the limit L going to infinity. So it has to be very sick theory that you change thread some flux, and the gap goes from finite value to 0. Yeah. Good questions. Okay, so right, so this is the surprise, at least naively, that a large set of gapped phases of lattice systems is described by topological quantum field theory. Okay, so here everything I said, I didn't specify any symmetry of the problem, but right off the bat, let me explain how to add symmetry to these definitions. So adding symmetry. So often we are interested in a class of Hamiltonians that have a certain symmetry, and in condensed matter physics, kind of the common symmetries that you encounter, well, particle number is conserved, right? Number of electrons in your piece of metal is conserved. We have time reversal symmetry if you don't apply any magnetic field. We have spin rotation symmetry if the spin-orbit coupling is neglected. And we have, on the lattice, we have the symmetries of the lattice. So we have translation symmetry, we have reflection symmetries, we have rotations, glides, and so forth. So these are all kind of symmetries you encounter often in condensed matter systems, and you'd like to enrich your classification, or you'd like to understand how the symmetries constrain your physics. So to begin with, let me start with the case when we have an internal unitary symmetry. Internal unitary symmetry. Okay, so the symmetry operations form some group G, and we require that the symmetry operation G be implemented on our Hilbert space by an operation like this, where Ui over G acts just on the site I on the lattice, and the ui's on each side satisfy the following group law. So such symmetries that act in this manner are called on-site symmetries. I think this is a term that Shaugan coined, on-site symmetry. Why this special form of symmetries? Why? Well, first of all, many symmetries that we are interested in condensed matter are of this form, say particle number conservation, U1 symmetry. But more generally, we'll see that for symmetries which are of this type, we can always couple the system to a flat background gauge field. Okay, so for it to be a symmetry, what property must the Hamiltonian have? Well, it must commute with U, or in fact, we require that each hi, or at least the Hamiltonian, can be broken up into hi's, where which commute with U for symmetry, for H to be symmetric. Okay, and then we can just extend the definition of a gap phase to a gap phase with symmetry by requiring H1 and H2 to be interpolated by some H of S, where H of S has this property for all S. Okay, so that defines phases with symmetry. Now, turns out that gapped phases in general are a bit too complicated for me, so I'm going to simplify things even more. I'm going to talk about a special class of gap phases, which we call invertible phases. And these are the phases that will have direct connection with Toft anomalies, as we'll see.
Sorry, question? Yes. So I just want to ask, are there any more conditions in the H1 and H2 being interpolated by HS? So the reason I ask this is because if you want to define two things as being in the same gap phase, in the approach of Kapustin, for instance, if you're looking at C-star dynamical systems, then there are some additional constraints of locally generated automorphisms on that C-star dynamical system that obey some kind of constraint that has to do with entanglement, I think.
Well, so first of all, nothing I'm going to say is going to be rigorous. Please keep that in mind. So taking this thermodynamic limit, all of that is actually very non-trivial. So somehow we're assuming that everything, all of those steps work out. Now, one thing I should add is that in general, maybe you start with a Hilbert space which looks like this, just spin a half on each side. Sometimes that might kind of not be enough maybe for you to realize all the phases. So I'd like to be able to kind of stabilize your classification. So you might want to allow throwing in trivial degrees of freedom. So you might want to start with H1 and say we add, we tensor with a Hilbert space V prime, let's say, with a Hamiltonian H0 on that Hilbert space that's of this form, and then we have this family of Hamiltonians on that enlarged Hilbert space, and then we go to some H2, which again has a trivial product state factoring out, and then we drop that. So you should be allowed to stabilize things like that. Yeah, but other than that, I don't see an immediate problem with the definition. Yes?
Is there an analog of these symmetry-enriched type phases for lattice symmetries? Of course, we cannot.
Yes, there are. And actually, it's a very interesting and rich subject. But somehow, it appears that there is what people call a lattice equivalence principle, that at least for a broad class of phases, classification of phases with internal symmetries and with lattice symmetries with the same symmetry group are related to each other. So somehow you don't lose too much generality by thinking about internal symmetries. Okay, so let me now define invertible phases. Which one? Oh, just behind? Okay.
But you have to be 1 meter tolerant.
Oh, wow, okay. Now it's gone. Thank you. Okay. Invertible. So first, I want to define an operation on phases of matter, which I'll call stacking. So stacking. So if I have phase A and phase B, I can form a stack of them. And the way you do it, well, just say this, just for easiness of visualization, let me draw them as two-dimensional, and then you just, so this is system A, this is system B, and you just put them on top of each other. So, think of each phase is realized on its own Hilbert space. So consider the tensor product Hilbert space, and consider the Hamiltonian, which represents this stack with kind of the sum Hamiltonian of the two phases, HA and HB.
So the lattices are two different lattices, or just put them...
That's right, that's right. They could be, I mean, you can make them both the same shape, or you can make them different shape, doesn't really matter, but what's important is that there is kind of, the notion of locality is preserved when you stack them on top of each other. Okay, and then...
in no sense they are in top of each other, right?
Sorry?
They are not in top of each other in any way, right? They can be like, they're different universes in some sense.
I'd like to keep the notion of locality, right? So somehow, if, let's say I have two square lattices, right? And, sites near the origin in the first lattice and sites near the origin in the second lattice will be close together when I stack them. That's I want to keep this notion of locality.
You're going to add some term in the Hamiltonian.
So far I just defined this stacking operation, right? And now, this is a Hamiltonian acting on this tensor product Hilbert space, and now I just use my equivalence principle definition of gap phases on everything that can be connected to this Hamiltonian via a gap path, and a gap path of Hamiltonians acting on the stack, not necessarily separately on each layer, will be in the same phase as A plus B.
And the Hamiltonian are local.
Local, yeah. So when I stack, I preserve this. I keep the notion of locality from each copy. Okay, so we say that a phase A has an inverse if there is another phase, call it minus A, with A plus minus A equal to 0, where 0 is the trivial product state. Right? So suppose you start with phase A and you find another phase minus A, such that first you stack them on top of each other, then you turn on interactions between the layers, local interactions, and deform the Hamiltonian such that the ground state is now just a tensor product Hilbert tensor product state on each layer. So that's 0, right? Remember, we defined this as the trivial phase. So the set of gap states that possess an inverse will be called invertible gapped phases. Let's see, where do we go now? Maybe I made a mistake by using the third board. Okay, let's go here.
There also is below another one.
Oh, okay.
This is just in there.
Let's. We can just write here. Set of gapped phases with an inverse equal invertible gapped phases. And in fact, these invertible gap phases form an abelian group under the stacking operation, where the trivial product state, trivial product phase, serves as the 0, and then each one has an inverse, just by definition. Form an abelian group. Abelian because clearly the stacking operation, the order in which you stack doesn't matter.
Do you have any symmetry in mind?
So right now I gave definition with no symmetries, but you can trivially extend this to invertible phases with symmetry, just by requiring that each phase has a symmetry acting on it, and then the joint action on this stack is the product of the two symmetry action, and you require that the Hamiltonian be a sum of local terms that commute with the symmetry. So we'll be interested in both invertible gap phases without symmetry and with symmetry. Okay, so not all gap phases are invertible. Not all gapped phases are invertible. An example of a phase which is not invertible is one which has a degenerate ground state. Let's say we have some kind of anion model or topological quantum field theory that has a degeneracy on a torus, finite degeneracy on a torus. Let me just write here. Thank you. At Perimeter Institute, they use a hockey stick as a pointer. So I don't know what the French.
Buttons to bring the boards up and down.
No?
Yeah, I think they have like mechanical.
I don't know what's the French equivalent of a hockey stick. Too soft. Okay. So suppose you have some phase where you have a degenerate ground state on some manifold. Most relevant, I think, most relevant is the torus, right? Because any system we can put on a torus. Okay, so suppose we have a k-fold degeneracy here and then a gap. So suppose this is your representative of a phase A, and suppose you try to find its inverse, right? So suppose you try to stack with something that has, I don't know, m-fold degenerate ground state. Answer, or as I say, addition. Right, so now the overall degeneracy after this stacking operation will be k times m. Degeneracy. Right, so no matter what I choose this putative inverse to be, the degeneracy will remain greater or equal to k. Now, as we deform the Hamiltonian, we are trying to find an inverse, so we are trying to deform into something that has a unique ground state, right? The trivial phase, trivial gap phase that has a unique ground state, which is just that product state. And so there is no way, so this has degeneracy 1 product state. There is no way to deform the Hamiltonian without closing the gap and the degeneracy jump from k times m to 1. Yes?
In high energy theory, sometimes people add ghosts to remove states. Could you imagine a lattice analog of that?
Well, so here I defined the setting for my problem, which is I have a Hilbert space, right, which has which is positive definite, and I have local tensor product Hilbert space, and I have a unitary Hamiltonian, Hermitian Hamiltonian on top of that. So ghosts are somehow something with negative norm. So I think ghosts, I don't know if everyone in the audience will agree, but it's some some trick to model a particular unitary theory, right? Here we are starting already with a unitary theory. You might. It's an interesting question. If your Hilbert space is not tensor product but has some local constraints or global constraints, how these classifications change. And general answer is not known. Yes.
It's not possible that the degenerate ground state kind of becomes a single state, kind of related with this question?
Well, it's unitary, right? So this have number of states below some cutoff doesn't change unless one of the states crosses that cutoff. Yeah, you would need the gap, right? So suppose one of the states lifts here, right? But that means that in that process, the gap between that state and this state went to 0, right? Which would violate our equivalence relation. And one of the states cannot just become null by unitarity.
Sorry, are there some more refined equivalence relations which also take into account the degeneracy of the first excited states?
Generally, we don't care about that. I think that becomes too refined. It's difficult to, what happens in the excited spectrum. At least the degeneracies in the excited spectrum are not so important, because you can kind of change the order of those excited states without having a phase transition, right? So if you think about, let's say, maybe more general definition of a phase that even goes beyond gap phases is you look at the partition function on some closed manifold, and you require the partition function to be analytic in the thermodynamic limit. Or the free energy to be analytic in the parameter that you are tuning. And if some level crossing happens in the excited part of the spectrum, that doesn't affect this analyticity property. Okay, so definitely not all phases have inverses. Say, phases described by an anion model with a number of anions greater than 1, which have a protected degeneracy on the torus, protected ground state degeneracy on a torus are not invertible. And in fact, by this argument, invertible phases must have a unique ground state on any spatial manifold. Invertible phases have a unique ground state on any spatial manifold. That means that they have no non-local bulk excitations, no anion excitations, right? Because once I have non-trivial anion excitations, I'll have protected ground state degeneracy on a torus, say.
Is it obvious that if something is invertible on sphere, it's also invertible on torus?
No, not at least in this. Well, okay. So, in which invertible, in which sense? So, if you think about equivalence of local Hamiltonians, right, that you can go from Hamiltonian H1 to Hamiltonian H2, preserving a gap, I think it shouldn't matter. You already taken thermodynamic limit. It shouldn't matter whether you found a path on a sphere or on a torus. But if you just want to count the ground state dimensionality, then that clearly doesn't work, because an anion model on a sphere will always have a unique ground state. Questions? So no.
So just repeat the previous question. So you're saying if we repeat this exercise on the torus, we take two Hamiltonians, we connect them, everything's perfect, the number of ground states is the same, gap doesn't close, just on one manifold, on the torus. Then you're saying your guess would be that on any other manifold, things would also be okay?
Yes. That's the guess, right? Just by locality.
I have a question. Is there a converse statement? So if you have a unique ground state, is that an invertible phase?
On any manifold. You're asking whether if I...
There's a converse statement. So if this is...
You want to ask, if I have a phase which has a unique ground state on any manifold, is it necessarily invertible?
Yes.
Well,
I get the sense that's taken for granted in the relativistic context.
I think certainly, your usual TQFTs wouldn't would satisfy that converse, right? And we really don't have many examples. I don't know of any example that would violate it. At least, maybe someone can. Anyone knows an example? Okay, proof by democracy. Okay. Right, so they have no anion excitations in the bulk. But what we'll see later is that they have interesting, yes?
So I think a counterexample would be an SPT protected by non-invertible symmetry. There it's non-invertible, but it's still one ground state.
Well, there you need to extend the whole notion, right, of what you mean by stacking and symmetry operation.
Yeah, so there's no inverse under stacking. But there is one.
So maybe I'll You want to speak up, Sal?
Oh, SPT protected by non-invertible symmetry.
What symmetry?
Non-invertible.
Oh, I see.
The classification isn't a group like.
But can you stack? I thought there's no diagonal.
You can just take the two T, I don't know, like you can just add the Hamiltonians together.
you also have to define how the symmetry then acts on the stacked theory, which might not be entirely obvious. Yeah. Okay, so not talking about non-invertible symmetries, talking about on-site unitary symmetries. Actually, unitarity we'll later talk about non-unitary time reversal symmetry as well. Anti-unitary is fine.
How the equivalence between Hamiltonians change in the presence of symmetries?
Right, so you just require that the Hamiltonian be a sum of terms hi, local terms, each of which commutes with the symmetry.
But then as you were deforming, you require that as a symmetry for any S in the...
So we fix the action of the symmetry on the Hilbert space once and for all, and then we work with that.
And then you require that as you deform H1 to H2, it's always a symmetry.
That's right. Okay, so we'll later see that when we go to the continuum and compute not only the ground state degeneracy on some spatial manifold, but compute the partition function on some space-time manifold, we'll see that actually these invertible phases have partition functions which are pure phase. Z of M, E of phi, M closed, where phi is just some phase. And we can add symmetry to this discussion, as I already noted. You can talk about invertible phases with symmetry. All the definitions go through. So let me, before continuing, let me just give you some examples of invertible phases with no symmetry in low dimensions. So let's start with phases of bosons. So here is the dimensionality. Here is the group, the abelian group formed by the phases, and here is the generator. So in 1 + 1 dimensions, no non-trivial phases of invertible phases of bosons. In 2 + 1 dimensions, we have an integer classification generated by the so-called E8 state, which has an edge with a chiral central charge equal to 8. In 3 + 1 dimensions, we have nothing. What about fermions? If you have a phase of fermions, then in 1 + 1 dimension, we now have a non-trivial phase, single non-trivial phase, so we have a Z2 classification. This is generated by so-called Kitaev wire. So we'll talk about this Kitaev wire in a lot of detail shortly. You'll become very familiar with it. Kitaev wire. 2 + 1 dimensions. We have integer classification again, which is generated by the so-called p+ip superconductor, which has an edge with a chiral central charge 1/2, just a chiral Majorana edge. And in 3 + 1 dimension, there is nothing. So these are invertible phases in low dimension with no symmetry. Invertible phases with no symmetry. And then for each symmetry group G, you can kind of play the same classification game. The classification becomes generally much more rich. We'll discuss some phases, some examples of phases enriched with symmetry shortly. Questions? Very good. So I kind of shoved this under the rug, but when we were defining our Hilbert space, right, actually, strictly speaking, the definition I gave is for the case of bosons. For the case of fermions, on each Hilbert space, on each side is graded, right? So there is notion of even operators with even fermion parity and odd fermion parity. And then when I define my terms, local terms in the Hamiltonian, all those terms must commute with the fermion parity operator for the problem with fermions. Yes. We will see that when we go to the TQFT description, those will be spin TQFTs and non-spin TQFTs. That is, TQFTs that you can define only on manifolds with spin structure or arbitrary manifolds.
So I have a question. Yes. Your spin structure for the spin TQFT have to be the same spin structure on the lattice system? Or how do we define the spin structure on lattice?
Excellent question. So, you know, it's not clear at all right now that a TQFT should emerge, right? Even in the bosonic case. And then you're kind of asking an even more subtle question. On, you know, when you're working on a torus, it's kind of clear that, you know, the spin structure or the boundary condition on the lattice should map to the boundary condition in the continuum, and then what twisting along the time cycle corresponds to. But, you know, people have written lattice Hamiltonians that you can put on, they typically commuting projector Hamiltonians that you can put on any kind of triangulation, and people introduced what it means to have a spin structure on those triangulations. But, you know, for a general model, we really only know how to put it on a torus. So again, yes.
Yes. Right. Is there any significance of the finite group versus non-finite?
We'll talk about that. Yeah. The topological theory that describes these integer ones, actually, strictly speaking, for a purist, is not topological. The partition function will depend on the metric, but in just kind of a rather simple way, through a gravitational Chern Simons term. Yes?
When you say that these gap phases form an abelian group, and then here when you the generator is what do you mean by the generator?
So this is the one in the, right? So this integers generated, there is a generator of the integers, and I'm writing kind of a phase that's in the equivalence, a state which is in the equivalence class of that phase. So this p+ip superconductor is some kind of Hamiltonian. Actually, it's a free fermion Hamiltonian that realizes that phase. Yeah. Good.
Maybe one question. So, an arbitrary QFT you can put in particular on a spin manifold. And so I feel there should be some sort of morphism between the bosonic and fermionic.
Yeah. So if you have a bosonic, theory, you can trivially convert it into fermionic theory. Just the partition function doesn't depend on the spin structure anymore. Going the other way, well, you can gauge the fermion parity, but that will generally not give you an invertible phase. Gauging fermion parity means summing over spin structures. But you're right. This way you can map. Yes.
And we know the answer for like general group, or there is a way to.
We will talk about it. So it's believed that these objects are in correspondence with bordism groups in various dimensions. And then it depends on whether you're good at computing bordism groups. For a general, okay, without symmetry, I think people know the answer. So just people know what the bordism groups on oriented or non-oriented manifolds are. So those corresponds to boson with no symmetry or bosons with time reversal. And I think spin bordism groups are also known in any dimension. If you enrich with the symmetry, it becomes much harder to compute the general bordism group in any dimension. But in low dimension, people can work it out. Yeah. So we'll talk about bordism, probably not in this lecture, but next one or. Yeah.
In the generator, you can also see from this bordism?
Yes. So you'll see all of this.
Is it obvious that if the inverse exists, it's 0?
Is it obvious that the inverse is unique? Well, because we showed that it has a group structure, right? So. Did you actually show that? Well, we showed that. By definition, an inverse exists, right? And but invertible phase is defined as one where the inverse exists, and then there is the addition. We define the addition operation, and we define the zero. So I think in a group, in a group, if you have an inverse, it's unique, right?
Or in other words, we could actually show that it is a group.
So what do you need to show? Oh, you need to show associativity.
Or like this doesn't need inverse.
I guess the zero should be
zero is unique, but like if you have a non-zero phase, is it obvious that inverse is unique?
Yes, you can simply take one of your inverses, add it to A, add it to the other inverse, and simplify in two different ways to see that the two inverses have to be the same.
I think it's just I think it's just property of a group, right?
Yeah, I agree.
More questions? Okay, so there is one caveat that I should make, which is when I'm writing down this classification, strictly speaking, I'm cheating. I'm really writing down the classification of topological field theory. So I'm only writing down classification of phases that are described by topological field theory. Does this miss something? Well, we know some examples that this misses, so I'll give you one example. So caveat. Miss phases not described by TQFT. And one example is, you take this.
Maxim, I don't think you ever explained what it means for a phase to be described by TQFT.
We'll see that in.
So you prefer to first describe what it means not to be described?
I'm going to give you an example. I'm first going to give you an example where this classification is incomplete, and then we'll talk more about explaining the classification. Yeah. So take one of these, let's say, p+ip superconductors in 2+1 dimension and form an infinite stack, right? Form a 3+1 dimensional system, which is just made of layers of this p+ip superconductor. Or it can, if you're working in the bosonic case, take a stack of this E8 2+1 dimensional phases, right? And each one has a chiral edge mode here. So this is an invertible phase, right? Because each layer is invertible. So the stack is also invertible. You can just invert it locally. But it's not part of this it's clearly non-trivial. You know, it has this gapless edge modes that cannot be gapped out, but it's not described by, it's not in our classification. The classification gives nothing in 3 dimension. Now, what's weird about this particular phase? Well, there is a preferred direction of stacking, right? There is kind of a very distinct direction, which is the 3rd direction along which I've stacked things, particularly visible on the edge, right? So I have these chiral modes going in the xy plane, and in each layer I have one.
But is it also it's a phase? Because maybe if you start introducing interactions between these levels, and there are infinitely many of them, maybe this is going to become trivial.
But you cannot get rid of the chiral central charge on the boundary, right? So if you think about L copies, right, the edge has chiral. If you think about it, if you reduce to 2 + 1 dimension, the edge has central charge L/2, and you cannot do anything with this central charge. So it's clear that this is a separate phase, but it's not described in the IR by any Lorentz invariant system, right? There's kind of very clear spatial direction here, which is the 3rd direction picked out. So we'll not be able to describe objects like this. Yes?
It's a very stupid question. But you talk about stacking this thing, but so stacking doesn't preserve the dimension of.
So here I'm overloading the term stacking. So before, when I talked about stacking, I really thought about stacking 2 copies, or finite number of copies of the system on top of each other. So I start with a d-dimensional state, and I end with it, and I think of the result as a d-dimensional state. Here, I'm really thinking about taking L copies and taking L to infinity, thinking of this as a d + 1 dimensional system.
So it just lies at this p+ip model.
That's right. So the notion of locality now involves also this 3rd direction along which I stacked. Yes?
Is it at least true that all the phases which are out of this classification can be constructed in some way like this stacking?
We don't really know. I think the belief is that this only starts in 3 + 1D. This kind of phases start to appear. So people call this non-liquid. I think Shougan again is the person who coined this word, non-liquid phase, right? Because it's kind of not isotropic. And you know, these kind of weird beasts are related to, say, these fracton phases that are kind of much more sophisticated than this, but the basic issue is already there in this simple example. Yes?
So yeah, maybe this state have a more general property that you cannot enlarge system by adding the tensor product qubits. So the RG is quite good. Maybe the invertible you considered over there, the system can be enlarged by dissolving the product states. For this stacked thing, or this fraction phase, the RG works differently. You cannot enlarge the system by stacking with, by adding product qubits.
You mean that if you add an extra layer?
No, if you add the qubits, try to enlarge. So suppose you have this kind of system. One have a size L, another have a 2L. The 2 systems cannot be connected by stacking with actual qubits in product space and then doing your RG, doing your deformation. You know, there's a way you need to connect a system with different size. Because if a system with different size, are they connected or not using your property? But to change the size, you can only allow to add the product state. And this system of different size are not connected by your definition and by adding the product state.
I see. Yeah. I see.
That's a meaning of non-liquid.
I see. So maybe that's a good way to kind of restrict to only phases that flow to TQ(t)s in the infrared.
I didn't quite catch the explanation.
So the explanation involved what happens, you know, how to connect systems of different size, and whether you can just throw in a product state. Let's say you want to grow the size by 1, right? Or maybe you want to add just one layer on top, right? Whether you can add a product state, 2 plus 1 dimensional product state in this case, and then change the interactions to kind of incorporate it into our system. Or whether you, in this case, you, instead of adding product states, you need to add p+ip state. Yes?
So if you consider this as a 3D system with translation invariance, is that now captured by the CFT?
Well, it's, you know, if we forget the symmetry, right, it's already not captured. So how can it be captured if you add symmetry?
Can I ask a question about this explanation before? Yeah. Is there a reason why they can't be connected by adding product states that they have extensive ground state degeneracy? This kind of.
Well, no, product state by definition has a unique.
Yeah, but I'm saying that these kind of phases typically have extensive ground state.
Well, this particular one doesn't, right? This one, if I instead of open boundary conditions, I consider here closed boundary condition, then there is a unique ground state. Okay. But you're right that the fracton phases that are some kind of more generalization of this have an extensive ground state degeneracy. Yeah.
Maybe we let you speak a little bit more than asking so many questions.
Well, it's good, but you know, really, this fracton field is a whole other area that I don't. I think there are many people in the audience who know much more about it than I do. So direct your questions to Sal. Okay. Good. So let me give you an example of perhaps, you know, at least one of the most simple invertible phases, which is this Kitaev arrow. So this is going to be an example of an invertible phase of fermions in 1 plus 1 dimensions. And we are going to have a very explicit lattice construction, and then we are going to learn how to take the continuum limit of that and really consider the system on an arbitrary space-time manifold. And then we are going to make a connection with the bordism. Okay, let's see. Okay, so consider the following Hilbert space. Consider you just have a chain in 1 dimension with n sides. And on each side, we have a fermion. So we have creation annihilation operators, Ci, Cj, with the usual anti-commutation relation. Okay, and so this is the Hilbert space. And on this Hilbert space, we're going to consider 2 Hamiltonians. One will be in the trivial phase. We'll have a product state, ground state. The other will be in non-trivial phase. In order to facilitate definition of these Hamiltonians, let me write this complex fermion creation and annihilation operators in terms of Majorana operators. That is, in terms of just real and imaginary components, or Hermitian and anti-Hermitian components. So let me define on each side operators gamma and gamma bar. Maybe this should be J. Such that these gamma operators are Hermitian, and same with gamma bar. And they square to 1. And gamma I, gamma j bar is equal to 0. Gamma I, gamma j is 2 delta ij. Gamma I bar, gamma j bar is 2 delta ij. Right, so this is just definition. And now we can kind of pictorially think of breaking up each side, each complex fermion operator into two of these Majorana. So I'm going to draw it as two sides. Let's do it. So let me draw it like this. Gamma 1 bar, gamma 2 bar. And here somewhere, gamma n bar. And consider first the first Hamiltonian, H naught. This will realize the trivial product state. And we can equivalently write this in terms of the C operators. Like this. So the ground state will have occupation number of fermions on each side equal to 0, right? So ground state satisfies Ci dagger Ci equal to 0, or equivalently I gamma I bar is equal to, on the ground state, is equal to -1. So pictorially, I'm kind of pairing these Majoranas in the following manner. And this is a product state, right? It's just on each side I have no fermion. So there's like no fermion in the system. That's the ground state. And it's gapped, well, because the excitations are obtained by changing C dagger C on some side to 1 from 0. So the gap value is 2. Gap is equal to 2. OK. So this is a representative of the trivial product state. What about the non-trivial Kitaev phase? Well, let's see. Where should we go? Let's maybe go here. Can people see here? Is it too dark? H1. I'm going to pair the Majoranas in a different manner now. Gamma j bar, gamma j plus 1. So this can be equivalently written in terms of the C operators in the following manner. So we have now terms that connect different sides when you write it in terms of the C operators. Cj, Cj, Right, so let's draw it again pictorially. So here is side 1, side 2, side 3, all the way up to side n. So this is gamma 1 bar, gamma 2 bar, gamma 3 bar, gamma n bar. And now I'm pairing my Majoranas like this. These get paired. These get paired. And then if I'm on a closed chain, right, then this is gamma n, gamma 1. So you see that, well, the ground state is again unique. The ground state is characterized by I gamma j bar on the ground state of this Hamiltonian at H1 is equal to -1. And again, excitations are obtained by flipping the eigenvalue of one of these operators, and the gap is equal to 2. Right? So if I consider the state on a closed chain like this, it's a fully gapped unique ground state. Sorry? Oh, gamma j bar gamma j plus 1. Correct. Sorry. Yeah. Okay. On the other hand, suppose we consider the Hamiltonian on an open chain. Exactly same Hamiltonian, except, let's see, now we want to go to n-1. So all the Majoranas in the bulk are again paired up, but we are left with this Majorana gamma 1 and Majorana gamma n bar that do not have a partner. So open chain gamma I gamma j bar gamma j plus 1 is equal to, or carries eigenvalue -1 for j equal 1 to n-1, but gamma 1 and gamma n bar are unpaired. So therefore, the ground state can have gamma I gamma 1 gamma n bar equal to +1 or -1. These operators I gamma bar always have eigenvalues +/-1. And here either eigenvalue gives you the same energy, because these operators are not actually involved in the Hamiltonian. Open chain I gamma 1 gamma n bar equal plus or -1. So we have a degeneracy of the ground state equal to 2. Right? The spectrum looks like this. we have a twofold degenerate ground state, then we have our gap, which is, again, in this case, 2. And then, well, OK. Doesn't matter what happens afterwards. OK. So we have on a closed chain, we have a unique ground state. On an open chain, we have a twofold degenerate ground state. Now, you might say this is twofold degeneracy, maybe just some accident of how you chose your boundary Hamiltonian here. Maybe we can perturb this Hamiltonian on the boundary somehow and leave this degeneracy. Turns out, though, that you cannot do this in the thermodynamic limit, right? So to leave the degeneracy, let's say try to do it in perturbation theory. Maybe you introduce some small coupling here and maybe also here. Can you do it in perturbation theory? Well, in perturbation theory, you would need to generate a term like this, right? But this is a non-local term. So you would need to go to nth order in perturbation theory in order to connect this end of the chain to the other.
Can I ask a question? Why do you have degeneracy 2 and not 4? Why can't you act just by gamma 1 on the ground state?
But it's only twofold degeneracy, right? Because
you consider acting with this operator gamma 1, and bar. But what if you just act with gamma 1?
If you think about the Hilbert space, right? You can, OK, there is a canonical way that I divide up my Hilbert space, which is on each side can be occupied or not. Now you can think about doing a basis change to a Hilbert space where I group the Majoranas in this manner, and then all of these ones are in a definite state, and then there is only one qubit formed by gamma 1 and gamma n bar which is left. So there is only twofold degeneracy which is left. Yes. Sorry. No worries. OK. So perturbations either on the boundary or in the bulk are only going to leave the degeneracy like this. They're still going to have an exponentially small energy gap. And in fact, you must have this degeneracy on an open chain as long as the bulk is in the non-trivial phase. As long as you don't have any phase transition in the bulk, that is, as long as you don't have any phase transition detectable on a closed chain. What about the boundary itself? Let's kind of think just about one end of this chain. You have a single Majorana on the end. Can you have a single Majorana in 0+1 dimension? The answer is no, right? In some sense, you have this twofold degeneracy, and it's split between the two ends. So it's like each end carries the Hilbert space dimension square root of 2. And this is, in some sense, the simplest example of an anomaly. Anomalous boundary dimension, so single Majorana, dimension of the Hilbert space is square root of 2. Okay, maybe in codes. But the point is that in a 0+1 dimensional system of fermions, the way we've defined the Hilbert spaces here and so forth, you cannot have a single Majorana. You always have some number of complex fermion modes. You cannot have a single Majorana like this. So this is in some sense the simplest example of an anomaly. In this case, you should think maybe of it as a gravitational anomaly of a 0+1 dimensional system. The general story will be that these invertible phases possess boundaries that cannot be recreated standalone in a lower dimension under the rules of the game that we are using with the tensor product Hilbert space and on-site symmetry action when we have symmetry in the game.
Sorry, this is a square root of 2 is unclear. Maybe it's a cultural difference, but this is a little bit unclear.
Okay, so it's just a mnemonic kind of. It's, you know, not to be taken completely seriously, but, you know, I'm saying that the two n's have degeneracy 2 combined together. So if you wish, you could assign degeneracy square root of 2, or, you know, partition function on a, if you go to a cylinder, partition function square root 2 to each end, but clearly there is something anomalous about that. You cannot have that in a standalone 0+1 dimensional system. Yes?
If you have a degeneracy of 2, does it violate the invertibility?
Well, but this is on an open, right? So on important thing is on a closed system, there is a unique ground state and a gap. So when you have boundaries, you can have you can have degeneracy. Yeah.
Also, do you have a more general definition of how a boundary is anomalous?
Well, you know, this is in some sense the question of the entire series of these lectures, and this is just the first example I'm giving you. But loosely speaking, something that's anomalous is something that cannot exist on its own in a lower dimension.
In what sense it is a gravitational anomaly?
Well, there is no symmetry in the game, right? So if you think about TQFT, if there is no symmetry in the game, then it must be a gravitational, and it's anomalous, it must be a gravitational anomaly.
Isn't this the fact that you cannot define fermion parity for a single Majorana?
Exactly. We will talk about it later when we go to the continuum description.
Can I ask a question? You take the ground state 1 and act on it with just operator gamma 1.
Yes.
What are you going to do?
You're going to get a ground state 2, right? Because gamma 1 anti-commutes with this operator. So you're just going to flip the parity.
No, but he's not acting with gamma times gamma bar. He wants to act just with gamma.
That's fine, right? So gamma 1 anti-commutes with this operator. So if you start in a state, right, it commutes with this, anti-commutes with this. You start in a state with, say, parity +1. You're going to get state with parity -1.
Sorry, my apologies.
No worries. Actually, let's talk about that. Let's talk about the fermion parity of these two states.
Yeah. What if you consider a semi-infinite chain? So you have only one gamma.
What does it mean? What does it mean?
To ask that question, that question is mean.
What does it mean?
What does it mean?
What that the question is mean.
Yeah.
What is the sound of one spall hitting itself?
Okay, so let's think about the fermion parity of these two degenerate states on an open chain. Fermion parity. Right, so the fermion parity of the entire system, -1 to the f, whether it's open or closed, is just -1 to the sum Cj dagger Cj. And this I can write as -I gamma 1 bar minus I gamma 2 bar. You can check that on each side. -1 to the fermion parity is just -I gamma bar. Gamma n bar. And now let me regroup this a little bit by moving this gamma n bar over to here. So I'm going to have -I gamma 1 gamma n bar minus I gamma 1 bar gamma 2 minus I gamma 2 bar gamma 3 I gamma n minus 1 bar gamma n. Now, both of my ground states of the open chain are eigenstates of all of these operators with eigenvalue +1. Yeah, +1. So when acting on my two degenerate ground states, -1 to the f reduces precisely to this combination. So the two ground states, two degenerate ground states of an open chain actually differ by fermion parity. One has even fermion parity, the other odd. Okay, now so I described this story for this particular Hamiltonian, which is very simple, and which could be, where is my Hamiltonian? Which could be solved exactly. You can consider more general Hamiltonians that are in the same phase, which is that they are smoothly connected. And what you'll find more generally is that, again, you'll find two degenerate ground states, and the fermion parity acting on these two degenerate ground states on an open chain, right? So we have our open chain 1 to n. You'll find that fermion parity breaks up on this on the ground state subspace into the action of operators gamma left and gamma right, which are localized on the left and right end of the chain, exponentially localized, but not necessarily localized to a single site, as we had in this toy exactly solvable example, where gamma left and gamma right both anti-commute with the fermion parity. And once you have such fractionalization, you can prove that the two states, the two ground states will have the same energy. Essentially, acting with gamma left, say, on one of the ground state, will switch the fermion parity and will give you the other ground state. Okay, so I think we are getting towards the end of hour and a half. Let me conclude the lecture by saying that many people believe that this phase has actually been realized in experiments.
Are you among those people?
So there are several proposed realizations, and I suspect that several of them are indeed realizations. So experimental realizations, let me very briefly mention this. So, okay, so we want a system of fermions. So you take a wire, thin wire, and one of the materials which is used is indium arsenide. And actually, if you look at the Hamiltonian we've written here, I might have erased it, but the Hamiltonian for the non-trivial phase that we've written, it had not only C dagger C terms, but also CC and C dagger C dagger. So this Hamiltonian doesn't preserve particle number. So it's a superconductor. It's, so to realize this phase, you actually must proximatize your wire with a superconductor. So what people do is they put superconducting aluminum on top of this. And, well, very schematically, before you put on the superconductor, the electrons in your wire, because of spin-orbit coupling in this material, they have a dispersion roughly looking like this, where this is the spin-down electrons and these are the spin-up electrons. Then you apply a magnetic field in the x direction, which is going to flip the up electron into down electron, and is going to open up a gap here in the band structure. And then you dope your wire or do something such that the chemical potential is in this gap. So this way, you're left in a spinful system just with one kind of branch of electrons, just one C=1 theory at the Fermi level, at low energy. And finally, once you put this superconducting aluminum on top, that actually opens up a gap at the Fermi level. Well, okay, so you're supposed to, because it's superconducting, you should double the number of degrees of freedom, kind of go to this Gorkov basis, but you open up a gap at the Fermi level, and that is a realization precisely of this Kitaev wire phase. Okay, and one of the papers that describes some strong evidence that this system realizes these Majorana modes is this one by the Microsoft Station Q team. Okay, so let me maybe stop here.
So, are there some last-minute questions, maybe? No?
If you just stack the Kitaev wires the same way that you did the p+ip, you just get a trivial.
You get a trivial. We'll discuss that next time. So, so that's the Z2 classification in this case. Yeah.
Sorry, I meant like the foliated stack, like the.
Yeah. That's also trivial, right? Because you can pairwise, at least if you don't insist on translational symmetry. If you stack two, you get trivial, and then you're just stacking trivial.
But I thought you said that you want to like keep them decoupled.
Well, but once you stack, you allow external coupling. Yeah.
Okay, maybe let's thank Max again. He had lots of questions on it.